In this video, we're going to learn about a key adjective in the calculus called continuity or being continuous. Before we get to continuity, let's look at examples of where a function is not continuous. There are three types. This first type is where a function's graph jumps from one y value to another y value at a specific location. So in this case, at -1, this graph jumps from a y value of close to -1 to a y value of 1. We call that a jump discontinuity. An infinite discontinuity, also known as a vertical asymptote, occurs when the graph of a function starts to shoot towards either negative or positive infinity as you get closer to a specific x value. In this case, x equals 1. And finally, we have certain functions with what are called removable discontinuities, which means that your function's graph looks real nice and then skips one little y value and then continues on. So it's not quite a jump because on both sides of this point there is a limit, but there's a point missing. And we call it a removable discontinuity because if we defined our function appropriately, we could fill the hole and make our function continuous. So those are three types of discontinuities: jump, infinite, and removable. So what is it that removes discontinuity from a function and makes it continuous? Well, loosely speaking, continuous is an adjective that would say I can draw a function's graph without lifting my pencil. And if you think back to those three examples, you have the jump discontinuity. I have to lift my pencil to go from there to there. The infinite discontinuity, I have to lift my pencil to get to the other side of the asymptote. And the removable discontinuity, I have to lift my pencil to skip the dot that's missing. Now, that's not mathematical, so we can't really use that moving forward, but that's a nice little mental picture for you to have in your head. Continuous means I can draw the graph without lifting my pencil. What does that mean mathematically? Okay, this is what the adjective continuous is going to mean for us. So, a function f is continuous at a specific location, let's call it x equals a, if the following is true. And there's many ways to write this, but I'm going to write it as simply as I can, and you might have eventually evolved to something a little bit different. So I need to have the limit as x approaches a from the left to exist, but I also need it to be equal to the limit as x goes to a from the right. So what does that mean in general? That means that there is a limit at x equals a. And I also need that to be the same as the function value at x equals a. Okay? If those three things are true and they're all equal to each other, then you have a function that is continuous. Okay? The limit part says that at a, I come towards a certain y value from both sides, and that y value is the same. And if that is the same as the y value of the function, then this dot gets filled in, and I'd be able to draw my graph through point A without lifting my pencil. Let's jump right into some examples. Decide if this function f is continuous at x equals 2. So our test is to test the two limits and the function value and to see if they're equal. So let's write those out one by one. The limit as x goes to 2 from the left of f of x, well, in this case I will use 3 minus x since x is less than 2. And that limit is going to be equal to, if I do a plug-in, equal to 1. The limit as x goes to 2 from the right, this time we'll use the function x over 2 plus 1 since x is bigger than 2. And we do a plug-in here, and we get 1 plus 1 or 2. Okay, at this point I can stop and say that f is not continuous at x equals 2. And the reason is those two limits are not equal. What would I see on the graph? I would see a jump discontinuity. At the left, I'd be approaching 1, and from the right, I'd be approaching 2. Next example. Decide if f is continuous at x equals 2. Okay, So I need to check three things and see if they're all equal to each other. The limit as x goes to 2 from the left of f of x. In this case, we'll use 3 minus x. We do a plug-in and we get a limit of 1. The right-hand limit as x goes to 2 from the right. We use x over 2 because x is larger than 2 when we're looking at a right-handed limit. And 2 over 2 is equal to 1. So far, so good. This means that the limit exists at 2, but this also needs to be equal to the function value. So what is f of 2? Function definition says that f of 2 is equal to 2. So what does that mean? These three numbers are not all the same, so f is not continuous at x equals 2. Why is that? The limit at x equals 2 is not equal to the function value at x equals 2. What will we see on the graph? Well, since the limit exists, the graph would come together at x equals 2. So I would see something like this. However, the dot that's supposed to fill this hole is at 2 instead of 1. So I'd see a removable discontinuity. Okay, AP loves problems like this that test your conceptual knowledge of this idea. It says find a value a such that f is continuous. In other words, force f to be continuous. So if f is going to be continuous, the only place that's in question is x equals 3. So we need three things to be equal. We need the limit as x goes to 3 from the left of f of x. In this case, f of x is x squared minus 1 because x is less than 3 when you're doing a left-hand limit. That needs to be equal to the limit as x goes to 3 from the right. In this case, we'll use 2ax. And that will need to be equal to f of 3. Okay, the limit as x goes to 3 from the left with a plug-in is going to be 8. The limit as x goes to 3 from the right, doing a plug-in. Remember, we're plugging 3 in for x, not for a. So we'll get 6a. And f of 3 is also 6a in this case. So I can really just focus on 8 is equal to 6a. And so solving that for a, I'm going to get a is equal to 8 over 6, or a equals 4/3. Any other value of a, and you'll get a jump discontinuity. This is the only value of a that will make these two parts of the graph of f come together. Now, you may be asking yourself, why do I care about a function being continuous? And the answer is, many of the facts that we're going to use in calculus are going to depend on a function being continuous. This is one of the first ones we talk about. We have three of these value theorems that you're going to experience in the course. This one's called the intermediate value theorem. Intermediate means in between. Okay? In between. So here's what it says. It says if f is a continuous function on a closed interval a to b. Those are x values. Now, we know what continuous means by definition, and we also know what it means kind of intuitively in our heads, right? It means we can draw the graph without lifting our pencil. All right, so if f is a continuous function, then the graph of f must cross, this should say, every y value, sorry about that, between f of a and f of b at least once. It's a very simple theorem, and it's pretty obvious, I think, when you think about it. But let's draw a picture, because the pictures help. So let's draw a as an x value and b as an x value. And let's say that this is f of a, because remember that's a y value. And let's say that this is f of b. All right, so let's draw some points now. Here's a comma f of a, and here is b comma f of b. Now, what do we know about this function f? We know it's a continuous function, which means, roughly speaking, I can draw its graph without lifting the pencil. Do I know what the graph looks like? I have no idea. There are many possibilities for what the graph of f could look like. One is just to connect these two dots with a line, but many other things could happen as well. But what conclusion can we make about the graph of f if it's continuous? Well, it must cross every y value between f of a and f of b at least once. Maybe more than once, but at least once, because it's impossible for the graph of f to skip y values if it's continuous. So if I think about drawing horizontal lines, that represent y values, my graph must cross every one of those lines that lie between f of a and f of b. Now, if you go past f of b, we don't know anything. Okay, the graph does not have to come way up here, but it might, and the graph could go below f of a. We don't know. So let's take a look at a specific example. Let's say you were told that a function f is continuous, okay, and f of 1 is -1 and f of 2 is 3. So let's draw a picture that represents what I'm seeing here. So f of 1 is -1 and f of 2 is 3. So what do we know? We know f is continuous, which means I can draw the graph of f without lifting my pencil and going from -1 up to 3. So must f cross the line y equals 0? In other words, the x-axis. Yes, I cannot go from a y value of -1 to a y value 3 without lifting my pencil and not crossing the x-axis. So that is a yes, and the reason is the intermediate value theorem. And we'll talk about how to express ourselves on the next slide. Must f cross the line y equals 1? Yes, the y value 1 is right here, and to go from -1 to 3, I have to cross that line, no doubt about it. Must f cross the line y equals 2? Again, 2 lies between -1 and 3, so yes, f must cross that line, so that's a yes. Must f cross the line y equals 5? The answer is no. It doesn't have to cross the line y equals 5, which is above 3, greater than 3. And might the graph of f cross the line y equals 5? Yes, it could. It's possible, but we're not guaranteed that by the theorem. Okay, there are too many unknowns in this case. Now, here's a more exciting example, I suppose. In 2008, my dog Ginger was 11 inches from nose to tail. Today, she is 24 inches from nose to tail. Was there a time when she was exactly this silly number, 13.2521 inches long? Okay, how do we express our answer? Okay, I think we know the answer is going to be yes, even though this seems like a ridiculous answer. There had to be a time where she was exactly this many inches long, even if it was just for an instant. Because a person's height is a continuous function. You don't just stop being or stop having height at any moment. Okay, so how would we express our answer here? Okay, I would say since Ginger's height is a continuous function, she must have been every height between 11 and 24 inches, which includes this really crazy number, 13.251. Okay, and the calculus fact that gives me this is the intermediate value theorem, which you don't necessarily need to reference in your explanation, as long as you referenced the hypothesis. What was the hypothesis? That's the if part. If your function's continuous. So that word needs to be in here somewhere. And we like to reference the two y values that we have to use as boundaries. In this case, 11 inches and 24. Every height in between those has to be met.